Hi guys, this is Mrs. Allison, and today we are going to talk about Lagrange multipliers. Now, what a Lagrange multiplier technique is a way to be able to maximize or minimize a multivariable function where there's some constraint on the values that we're allowed to use. Okay, so picture what this looks like. We have some function, some surface in space, and rather than just including all of the values, we're going to constrain that function by restricting the area that we're able to look at. And what we're going to do that constraint is we're going to call that f of x, or sorry, g of xy equals some constant. And so what that might look like is we're looking for the points where the contour lines of f and the contour lines of g, if we bring them down to 2 dimensions, we're looking for where the level curves intersect. We're looking for where those contour lines are intersecting. And more importantly than that, when we want to talk about maximizing or minimizing that function, what we're looking for is we're looking for where the level curve is tangent to the constraint. Okay, so we're looking for where not only they intersect, but where they're tangent to each other. So at right, there's an example. So right here we have an example of a set of level curves. So if I have some surface in 3 space, and I were to flatten it down and make some level curves of this particular function, we'll say these are our level curves, right? This is where f of xy equals 7, this is the curve where f of xy equals 8, and so on. Well, then the constraint that I have is that I want to look for the maximums or minimums that of that function that fall along this curve. Okay, along this constraint curve. So what we're really looking for is where these level curves are tangent. Okay, so I'm just going to write that so we see that. Where level curve, I guess it would be, is tangent to the constraint. That's what I'm looking for, where they intersect, where they're tangent. So if we look at this, the point that we can see where they're tangent is the point 10. It says, what is the value of c in this figure where we maximize f of xy subject to the constraint g of xy equals k? And that point would be 10. And we can see that that's because that's along the level curve. Okay. Well, what I want you to do is think about the gradient field of the level curves. If you remember what a gradient is, a gradient vector, if you remember, gives us the directional derivatives. It gives us the, oh my goodness, what am I trying to say? It gives us the perpendicular, they are perpendicular to the curve at that point. It's like the quickest way off of that curve, if you remember talking about the gradients that way. It's like the fastest way we can get off that curve. It's the direction of maximum ascent. And so when we talk about these gradient field on the level curves, we know that gradient vectors are always perpendicular to that curve at the point. So if we were to look at this gradient field and maybe draw some on here, we might, and I don't really know how far it is, but we know that the gradient field might look something like this, where each of the gradient vectors are perpendicular to those level curves. Now, if we think about the gradient field of the constraint, so if we look at this constraint and we think about the gradient field here, maybe the gradient is a little bit bigger, but the gradient field here would be perpendicular to that curve at that point. Now, why is that important? If we're talking about the fact that the place where the value of c, where there's a maximum, where it maximizes the function, if we're looking at that place, what can we see? What we can see is that that place is subject to the constraint when the gradient vectors are parallel. Notice if they're both perpendicular to that point and those points are tangent, then those gradient vectors are going to be parallel. So what we can say, what do we know about parallel vectors? We know that for parallel vectors, that they are equivalent to each other by some scalar, right? So we can say that the vector for the gradient of f, our level curve, is equal to the gradient of g, that constraint curve, at some point x naught, y naught, where the gradient of g is multiplied by some scalar. Now this Greek symbol right here is lambda. Now I'm wondering if it has a b. Pretty sure it does. Lambda. Yeah. You know how when you look at something and sometimes it looks wrong? It currently doesn't look right, but I know it is. It is lambda. And that scalar is what we call our Lagrange multiplier. Now we're looking at this in 3 space. We're looking at this with a function of 2 variables, but this could easily be done with a function of 3 variables as well. We're going to focus on 2 variables for right now. I think I have one example later where it's 3 variables, but we're going to focus on 2. That lambda is called the Lagrange multiplier. And when we're deriving Lagrange's method, we're going to assume that the gradient of the constraint cannot be the 0 vector. Okay, so let's look at the method of Lagrange multipliers. The method that we're going to use for Lagrange multipliers to find the maximum or minimum values for some function subject to the constraint is that we're going to find all the values of x, y, and z and lambda such that the gradient of f is equal to lambda times the gradient of g, and at the same time g of xy is going to equal k. What that's going to give us is a system of equations, and what we're going to do is we're going to evaluate the points, the xy points that result from doing that system of equations. We're going to evaluate them to find our absolute max and our absolute min. Okay, so we're going to look at finding the extreme values using Lagrange multipliers 2 different ways on this first example. We're going to do it using Lagrange multipliers, and then we're going to do it using substitution, just so you can see the difference in the similarities between the 2. Okay, and I have an example of the graph. We'll look at that in just a moment. So to use the method of Lagrange multipliers, we need to find the gradient of f. And what we know, let's just call this method 1. Method 1, we'll call it Lagrange. What we know is that the gradient of f is really just a way to organize our partial derivatives. So the gradient of f of xy is equal to the vector that is represented by the partials with respect to x. So the partial with respect to x for f would be 2x, and the partial derivative with respect to y, which would be 4y. And then we're going to find the gradient of g of xy, our constraint function. And again, it's a gradient, so it's going to be the organization of the partial derivatives with respect to x and y. So the partial with respect to x is 2x, partial with respect to y is 2y. All right, now because these are parallel vectors, we know that the gradient of f needs to equal lambda times the gradient of g. So to set this up, we're actually going to set this up based on the components, the two partials with respect to f and the partial with respect to x and the partial with respect to y. So my first equation that I'm going to set up would be 2x has to equal lambda times 2x. The next equation that I'm going to set up using that same idea is that 4y needs to equal lambda times 2y. That's what the definition of the Lagrange multiplier says. That's the method that we're using. And now it's a system of equations that I need to use to find the values of x and y in this case, and lambda. So solving this, I can see that in this first example, x needs to equal lambda x, which means x minus lambda x equals 0, which means x times 1 minus lambda equals 0. So x has to be 0, and 1 minus lambda needs to equal 0. And so I get that lambda equals 1. And I'm going to come back to those two in just a second. Now you'll notice that I didn't solve this second part of this. I didn't solve for y just yet, and I'll explain why I didn't solve for y, although we can. Sometimes we'll need to do both, but in this case I didn't. So here's what I'm going to do now. What I'm going to do with this x equals 0 is I'm going to plug this into the constraint to solve for y. Plugging this into the constraint means that we get 0 squared plus y squared equals 1. So y equals plus or minus 1. This means, and again I'm going to organize my thoughts very similarly to how we did the absolute max and min before. X is going to be 0 and y is going to be 1. X is going to be 0 and y is going to be negative 1. Maybe we'll do those in green since that's the number we chose. And if we plug those in to our original function to figure out the value, we are going to get 0 plus 2 times 1, so 0 plus 2. And we're going to get 0 plus 2 times negative 1 squared, so 0 plus 2 again, so we get 2. Now, I have this funny lambda there. What am I going to do with that? Well, what I'm going to do, because the only other equation that I have with lambda that I haven't used yet, is I'm going to plug this into my 2y equals lambda y. Well, I didn't simplify this one up here. This is 2y equals lambda y, just simplifying that equation. So I'm going to plug that into 2y equals lambda y. Okay, and plugging lambda equals 1, we get 2y, let's go back to red, we get 2y equals y. So the only way that I get this is that if y equals 0, there's no other number that I can multiply y by 2 and have it equal just y. Now what we're going to do is plug this into the constraint. So once I've found what y is, I'm going to plug that into the constraint. And plugging y into the constraint, we get x squared plus 0 equals 1, which means x equals plus or minus 1. And so we would get the 2 points, positive 1 with 0 and negative 1 with 0, and substituting those into my original function, we get 1 and 1. Okay, so what we know now is that these two together must be my absolute max because they are my highest value, and both of these points will be my absolute min because they're my lowest value. So now let's look at that in terms of the problem below, the picture below, just so we can see what it looks like, and then we'll go to method 2. Okay, looking at this picture below, I just want to show you what it might look like if we were to take these curves and flatten them. So the function f of xy equals x squared plus 2y is this elliptic paraboloid here. And if we were to project this constraint, this x squared plus y squared equals 1, which is a circle down on a two-dimensional graph. But if we project that up on our curve, it's going to look a little bit different. It's going to have kind of these weird motions as it moves along the curve. But if we take the level curves, these ellipses, so picture these ellipses here. Here are my level curves, the red. Actually, there's some in black too. I'm not sure why. But if we take these level curves, because those ones don't have a max or min on them, I see it now. And then we project the constraint, we'll do that in blue on this one. We can see that the places where the level curve is perpendicular to, that's not what I mean, where the level curve is tangent to the constraint curve, you can see those points along here. We talked about the absolute max being at 0, 1 and 0, negative 1. And then we talked about the absolute minimum being at 1, 0 and negative 1, 0. And you can see those on those level curves. So that's what we're looking for. We're looking for the place where the constraint curve is tangent to the level curve. And then we're looking for the place that have the absolute max and absolute min in this example. Okay, let's go back to this same example and let's look at it just from a different lens. Now let's look at this using substitution. Okay, when we use substitution, what we're going to do is we're going to use the constraint to solve for one variable. I'm going to abbreviate variable. And so let's say we get x squared equals 1 minus y squared. I'm actually going to leave it x squared and I'll show you why. Because I'm going to substitute this back into my function, f of xy. So instead of xy in here, instead of it being x squared plus 2y squared, I'm going to put in the 1 minus y squared plus 2y squared, plus 2y squared. And I'm going to simplify this. Simplifying this, I get 1 minus 2y squared plus y squared plus 2y squared. So we get 1 plus y squared is my function f of xy when we substitute that in. Okay, well, we know that max and mins occur at critical values, and critical values happen when we take the derivative and set it equal to 0. Now, the reason we made that substitution is so we're not taking a partial derivative at this point. So if we take the derivative of f, we get 2y, and we know 2y equals 0 when y equals 0. So going back into my equation, we get x squared equals 1 minus 0, which means x squared equals 1, which means x equals plus or minus 1. This should look familiar to you. We've already done this point. We used this point before in the red. Well, then I would have to do this again. So I would have to use the constraint again, and this time I'm going to solve for y squared, and I would get y squared equals 1 minus x squared. And again, I would make a substitution. Not quite as clean this time because I would get plus 2 times 1 minus x squared. Simplifying this, we'd get x squared plus 2 times 1 minus 2x squared plus x squared. Combining like terms, we're going to end up with, let's see, 2 minus 4 plus 2, so minus 2 plus 1 would be minus 1. So we get 2 minus x squared. That was a lot of me saying random numbers. And again, I would take the derivative here and we'd get negative 2x. And then I would get x equals, or set that equal to 0. and I'd get x equals 0. And substituting that back in, you can see we're going to get y equals plus or minus 1. So really, you get to choose which method makes the most sense to you. I think the Lagrange multipliers in this particular case, maybe not as straightforward as just substitution, but once you get the hang of it, it is going to make your life a lot easier. Now, not all methods can use, or not all equations can use substitution. So let's look at a couple more. All right, let's revisit an example that we did yesterday. So the example asked us to find the absolute max and min values of the function f of xy equals 2x cubed plus y to the fourth on the region that was a circle, if you remember that one. I think it was the last one we did. We found the critical value 0, 0, and you can go back and review how we did that. And we also found the following points on the boundary that yielded the maximum and the minimum. And we said the absolute max was 1, 0, 2. And we said the absolute minimum was 1, 0, negative 2. I feel like that was supposed to be a negative 1. Shoot, I think it was. Hold on. Yes, this should have been a negative. I just went back and checked, but I think it was a negative 1, 0, 2. 1, 0, negative 2. All right. So remember we found that. Let's look at it using the Lagrange multipliers and just see what it looks like and how we would go and be able to find the same values using the Lagrange multiplier method. So if we found the gradient of f of xy, we would get 6x squared, comma 4y cubed. That would be my vector for f, and my gradient for g would be 2x, comma 2y. And so using the Lagrange method, we would get that 6x squared needs to equal lambda times 2x. And we would get 4y cubed needs to equal lambda times 2y. Okay, and so now I'm going to go through and solve. And I think I will solve for the x first. And moving the 2x over and dividing by 2, let's just simplify this. We get 3x squared minus lambda x equals 0. So let's factor out an x, and we are left with 3x minus lambda equals 0. So we get x equals 0. That's going to be the easy one. And we're going to get 3x minus lambda equals 0, which means lambda equals 3x, and we're trying to solve for x here, so x equals lambda over 3. All right. The reason I said this is the easy one is because we can take this and plug it into our constraint. And remember, our constraint was that circle. So we would get 0 squared plus y squared equals 1, and y equals plus or minus 1. Okay, we knew those points. We knew they were there. So let's go back and put them in our table. And remember, this one had quite a few points. xy, f of xy. So we had x is 0, we had positive 1. X is 0, we had negative 1. And when I plug those back into my function, I get 1 for both of them. Okay. Hang tight to that x equals lambda over 3. We're going to use that in just a moment. Now, when I go back to my y equation and I solve this one, I'm going to get 2y cubed minus lambda y equals 0. Factor out a y just like we did before. We're going to get 2y squared minus lambda equals 0. So y equals 0 and 2y squared minus lambda equals 0. I probably should have done these in the color that I did that with. So with this y equals 0, I can plug this into my constraint and we get x squared plus 0 equals 1, which means x equals plus or minus 1. Again, we knew these points, but let's just reiterate. So we have positive 1, 0, negative 1, 0, and when I plug those in, I get 2 and negative 2. But I still have this piece right here that gives me 2y squared equals lambda, and we get y squared equals lambda over 2. Now the reason I got both of these in terms of lambda is because I'm going to use these to find, I'm going to use these to substitute into my constraint equation, just like we did with the x equals 0 and the y equals 0. So here we have lambda over 3 x squared plus y squared. Well, I already know what y squared is. I know it's lambda over 2. Notice we didn't solve for y in this problem. We just solved for y squared. And that's going to equal 1. So we get lambda squared over 9 plus lambda over 2 equals 1. And let's multiply everything by 18. So we get 2 lambda squared plus 9 lambda equals 18. 2 lambda squared plus 9 lambda minus 18 equals 0, and I'm going to factor and solve. So I get 2 lambda minus 3 lambda plus 6, which means we get lambda equals 3 halves, and lambda equals -6. Now remember, we're using these to be able to figure out what x and y could also be. And if you look back at your notes from yesterday, you'll see we went through and did this by solving for x and solving for either x or y in the constraint equation and substituting it into my function. So this is just another method to be able to do that. So if lambda equals 3 over 2 and x equals lambda over 3, then x equals 3 halves divided by 3, which means we get 1 half. And now I'm going to take that lambda equals 3 halves and plug it into the y equation that we got, which was y squared equals lambda over 2. So y squared equals 3 halves over 2, which means y squared equals 3 over 4, which means y equals plus or minus root 3 over 2, or root of 3/4, which simplifies. Well, we knew that from before. We got those values before, where x equals 1 half and y equals positive root 3 over 2, and x equals 1 half and y equals negative root 3 over 2. Those are in that boundary region, so we're good there. But I have one more part to this. I have when lambda equals -6. And when lambda equals -6, x would equal -6 over 3. And -6 over 3 is -2. But this is outside of the domain, or it's outside of that constraint, that region. So therefore I don't even need to consider it. Now we already looked at these values, and we know if we plug it into the calculator we get 13/16. So we know that our max and our min are still the same two values. They shouldn't change. Here we have our absolute max and our absolute minimum. Notice we're not checking for local, just absolute. But this would be what it looks like to use the Lagrange multipliers technique for the same problem. All right, now let's look at a word problem. This problem says that we want to find the points on the sphere x squared plus y squared equals, x squared plus y squared plus z squared equals 4 that are closest to and farthest from, read, maximum and minimum distance from the point 3, 1, -1. Okay, so what we're going to do is we are going to find or use the distance formula here. But since we're doing it with respect to the point 3, 1, -1, I know that my distance is going to equal the square root of x minus 3 squared plus y minus 1 squared plus z plus 1 squared. Now, just for the ease of dealing with partial derivatives here, the result will really be the same if we maximize d squared instead of d. if you want to try your hands at those partial derivatives with the square root, I think it would be fine. It should work out the same. But in this instance, it is okay to just use the idea of d squared here. So that's what we're going to look at. Now, if we look at our function, we're going to let our function f of x, y, z be this function that is d squared. So then when we take our gradient of f, our gradient of f here is going to be 2 times x minus, that's a 3, not a 1. And then 2 times y minus 1, and 2 times z plus 1. And then the gradient of g, our constraint, well, the gradient of g, our constraint, is the sphere. The sphere is what's containing that point. So we're going to do 2x, 2y, 2z. So when we set this up, we're going to really create a system that we're going to need to solve. We're going to get 2x minus 3 equals lambda times 2x. 2 times y minus 1 equals lambda times 2y. And then 2 times z plus 1 equals lambda times 2z. So simplifying each of these, I'm going to get x minus 3 equals lambda x. Let's combine like terms. So x minus lambda x equals 3. So x times 1 minus lambda equals 3, and x equals 3 over 1 minus lambda. Okay, I'm going to take a little bit of shortcuts on these. You can verify the math, but if we did this one, we're going to get y minus lambda y equals 1, so therefore y equals 1 over 1 minus lambda. And similarly here, z plus 1 equals z, lambda z, and therefore we get z minus lambda z equals 1, and so then we get z, that would be a negative 1, z equals negative 1 over 1 minus lambda. Okay, so using the constraint, now we're going to go back into the constraint and we're going to take each of these lambda values and we're going to plug them into our constraint equation. Well, our constraint equation is that sphere. So I'm going to take each of these into 3 over 1 minus lambda squared plus 1 over 1 minus lambda squared plus negative 1 over 1 minus lambda squared equals 4. So we get 9, 1 minus lambda squared, plus 1 over 1 minus lambda squared, plus 1 over 1 minus lambda squared equals 4. Look at that. My denominators are all the same, so now I get 11 over 1 minus lambda squared equals 4. So solving, we get 11 fourths equals 1 minus lambda. 1 minus lambda equals plus or minus root 11 fourths, or 11 over 2. So lambda equals 1 plus or minus the square root of 11 over 2. Okay, well now what I'm going to do is I'm going to take this lambda here and I'm going to substitute it back into each of these values. And you can verify the math if you would like, but when I substitute these back in here, so for example, x, we're going to get plus or minus 6 over root 11. Y is going to equal plus or minus 2 over root 11. And z is going to equal, it's opposite. I'm going to write it opposite. I know that looks weird. I know plus or minus is really still plus or minus, but with it being negative 1, when it's going to switch that plus or minus. Okay, now what we're going to see here is that we have 3 points. We have the points, the x, y, and z, because we're looking for points on the sphere. we have the point 6 over root 11, positive 2 over root 11, and negative 2 over root 11. That's why we wrote it the wrong way. And then we have the point negative 6 over root 11, negative 2 over root 11, and positive 2 over root 11. And if we plug these into our constraint, into our function, what we're going to be able to see is which one is the maximum and which one is the minimum. Okay, we can see what will happen is this point right here will be our minimum, and this point will be our maximum. Now, I did take some shortcuts on there. It would be good if you want to verify the algebra on that, just to make sure you understand where all those values came from. But that is the method of Lagrange multipliers. The point of it is to be able to maximize or minimize. It's like an optimization problem with a constraint. And so that is where Lagrange multipliers are used. If you have any questions, feel free to pop on and ask me any questions. Otherwise, we will see you soon.